Bam! Mr. Tarrou. In this math lesson, we're going to do two examples in the beginning of simply reviewing how to solve quadratic equations with factoring, because, well, that's where most of my students struggle. We're then going to look at our solutions, look at the coefficients of these quadratic equations, and come to the realization, along with the little green board down here summarizing it for us in a statement, that there is a relationship between the sum and the products that we're going to get from these polynomials and the coefficients that are in these equations. We're then going to use that relationship to look at the equation of a quadratic and evaluate some expressions that involve the sum or the roots of these quadratics without actually solving for those roots. And the cool thing here is it allows us to answer some questions beyond just simple solving of quadratics that we've had before. And in an upcoming lesson, we're going to extend this idea to not just the sum and product of roots of quadratics, but actually at the core concept that's in this lesson, it actually extends to all polynomials. So let's get started first by reviewing how to factor and solve. So we have here a quadratic with a leading coefficient of 1. We have a constant which is negative, set equal to 0. And we're going to factor this by simply looking for factors of our constant, which is negative 12, that add to the middle term. Our factors of negative 12 that actually add to be negative 4 are going to be x minus, and so a factor of negative 6, and then we have x and a factor of positive 2. So we have our factors of our first term going in the first two blanks of our two factors here, the factors of our constant going in the last two blanks. And if we want to double check this, we're just going to simply distribute this back together. We have x times x is x squared, x times positive 2 is 2x, negative 6 times x is negative 6x, and of course negative 6x plus 2x is equal to negative 4. And we have that negative 6 times 2 is negative 12. Of course, we're going to set each of these factors now equal to 0. And end up with x is equal to 6 and x is equal to negative 2. Now, the whole point of this lesson is to not just talk about solving quadratics and not even just necessarily looking at the core roots, but what do they add up to? Well, the sum of 6 and negative 2 is equal to 4, and the product of 6 and our other root of negative 2 is equal to negative 12. Well, especially since our leading coefficient is 1 here, or basically our coefficient of a in our quadratic equation, we have that the sum of our two roots is coming up to not our middle coefficient here, but it seems like it's just the opposite. And the product of our two roots is equal to our constant. But with our leading coefficient equal to 1, we're not getting the complete picture here about the relationship of the sum and the product of our roots for a quadratic. So let's take a look at this example. Now with this example, we have a leading coefficient which is not equal to 1. So without being forced to do trial and error, or just a little graphical trick that sometimes we see in our algebra books now, we're going to go through the process of reviewing factoring by grouping that is going to allow us to solve this quadratic without trial and error. And that is going to be taking our leading coefficient and our constant. We're going to multiply those together and get some kind of product. Well, 6 times negative 10 is negative 60. Now, we're going to be looking for factors of this negative 60 that add to the middle term of negative 11. And we do have a product which is negative, so we're going to have to use factors, of course, that have different signs. We have something like negative 60 times 1. We have 2 times negative 30. That adds up to be negative 28, nowhere near negative 11. But we could use 4 and multiply that by negative 15. Now, 4 times negative 15 is equal to the negative 60, but the really not negative 6, but negative 60. But the real magic here is that negative 15 plus 4 is equal to negative 11. That's matching here our middle term. So we're going to With the product, the factors of our product that we got by taking the leading coefficient and the constant, multiplying it together, the fact that this special set of factors of negative 60 also add to the middle term, or basically coefficient, which is negative 11, we're going to use that to rewrite our trinomial as a 4-term polynomial. And we have 6x squared, we have minus 15x plus 4x, we have a minus 10 is equal to 0. And now that we have our trinomial written as a 4-term polynomial, we can factor by grouping, as long as this process over here in orange has worked out and we've done it properly. So we're going to look at the first 2 terms separately and realize that we can take out a factor of 3 and x. So we're going to have a 3x. 6x squared divided by 3x is equal to 2x. We have 15x divided by 3, which is going to give us negative 5. And out of our last 2 terms here, we can factor out a positive 2. So we have plus 2. 4 divided by 2 is 2, so we have a 2x. Negative 10 divided by 2 is negative 5, equals 0. And we have this one plus sign separating these 2 big terms. Basically, there's a term on the left and the right-hand side of my red dotted line. Each of these 2 terms have a common factor of 2x minus 5. So if we take that common factor of 2x minus 5 and factor that out, well, out of our first term, if we take out that 2x minus 5, we're just left with a 3x. And for our second term, if we take out that 2x minus 5, we're left with a 2. And now we have, this quadratic equation, degree of 2, with a leading coefficient other than 1, we've been able to factor it without having to do any kind of trial and error. That's all I was taught when I was in high school, many, many years ago. You can see all the gray hair. If you multiply this back together to double check it, you will have our original trinomial. Of course, now we're going to set each of these equal to 0 and finish solving. Subtract both sides, or add both sides by 5 and divide by 2. And here we're going to subtract by 2 and divide by 3. And we have these 2 roots here. So we're going to look at the sum. So we have 5 halves plus negative 2/3. We're going to need to find some common denominators. So we're going to multiply the second fraction by 2 in the numerator and denominator, and this first fraction by 3, giving us 15 minus 4 over the common denominator of 6, and we have 11 over 6. Now, the sum of our 2 roots, see, we have 11, almost, negative 11 is our coefficient of b, and we have 6, which is our coefficient of a. And over here, we had the sum of our 2 roots gave us 4. Well, it looked like we were just looking at the opposite of the middle term, but that's just simply because our leading coefficient is 1. So really, this 4 is equivalent to taking the opposite of our middle coefficient and then dividing that by our leading coefficient of 1. Or over here, our 11 over 6 is the equivalent of doing the opposite of or taking the opposite of our middle coefficient b and dividing it by our leading coefficient, or coefficient of a. So, whoops, thinking about what I'm about to show you here is a sort of summary statement. The sum of the 2 roots of a quadratic is equal to the opposite of the coefficient of b divided by the coefficient of a. Now, if we look at the roots multiplied together, well, if we look at x sub 1 times x sub 2, then we're looking at 5 over 2 times negative 2 over 3, giving us, with the 2's canceling out, negative 5/3. Well, yeah, I'm actually kind of hiding the relationship here because I've already reduced this, this product as I've multiplied. So let me just really make this obvious. 5 times negative 2 is negative 10, and 2 times 3 is equal to 6. the product that you get from the two roots of your quadratic are equal to the, well, negative 10 divided by 6, actually looking at just simply the quotient of c over a is what you get when you look at the product for the two roots of a quadratic. And that's what we're going to use to really look at the main three examples of our video here. We're going to be analyzing some products and sums and squares of the roots that we would be getting from a quadratic equation without actually solving the quadratic equation. So for quadratic equation, ax squared plus bx plus c equals 0, as long as a, b, and c are elements of the real set, the real numbers, and a is not equal to 0, because then you would not be dealing with a quadratic, but a linear function. With the roots of x sub 1 and x sub 2, the sum of those roots is equal to the opposite of coefficient b divided by coefficient of a, and the product is equal to c over a. We are just going to be looking at this as just an algebraic evaluation of some requested expressions. This does extend to more than just second degree polynomials, but third, fourth, and fifth, and 10th, basically all polynomials. This idea can be extended to it. And you'll see questions on possibly like an IB exam that would be rooted in the foundation of knowing how or what the sum and the product of roots yield in terms of coefficients of a given polynomial. First example coming up right now. And for our first example, given the quadratic whose roots are equal to x sub 1 and x sub 2, find the indicated expression without actually solving the equation. Yep, I felt that it was so important that I still went ahead and reviewed with you how to solve quadratics, especially when that leading coefficient is not equal to 1, with factoring, even though we're actually not going to solve this quadratic to answer this question or basically evaluate this expression or any of the expressions that were given in the next three examples. I wanted you to see that review of factoring. It's really, really important, and a lot of my students struggle with it. And I wanted to see for yourself through a couple of examples, not proofs, but with a couple of examples, that relationship of the sum and the product of those roots and the coefficients that are within that quadratic. And we are just starting with quadratic, but at its core, these relationships can be extended to higher order polynomials as well that wouldn't be that easy to solve, especially here. We already know how to solve it. It's very quick. But at any rate, we're going to evaluate 2 over x sub 1 plus 2 over x sub 2 without actually knowing the roots that we could just easily substitute in here and get the same answer. What if it was a fourth degree and I didn't want to actually solve that higher order polynomial? I could still evaluate this expression. So don't resist solving that quadratic, even though we can easily. The relationship of our roots to this polynomial and the coefficients is based only on sum and product, not subtraction, not division. So if I can't rework this expression a little bit to develop a sum and product of these roots of x sub 1 and x sub 2, we're not going to be able to evaluate it, at least not without relying on solving this. So how are we going to manipulate this expression to create some sums and products of roots? Well, just try something like you did in your geometry 2-column proofs or your trig proofs in pre-calculus or trigonometry. Just do some algebra and see if something nice happens. Like we have two terms. Maybe we could add these two terms and make one fraction. That requires multiplication through the process of finding common denominators. Maybe that'll help. So we have a factor, or a factor of x sub 1, a factor of x sub 2. We're assuming these have no common factors because, of course, how would we know? We're going to multiply the numerator and denominator by x sub 1 here because anything divided by itself is 1. So we're just going to change the way it looks. We're going to multiply the numerator and denominator by x sub 2 over here. Again, because anything divided by itself is 1, we're just going to change the way it looks. What do we get? We have 2 times x sub 2 plus 2 times x sub 1. That's our numerator. And I'm going to write a big old fraction bar because, well, we just created that common denominator that we needed. There's the product in the denominator that we need. So ultimately, this is going to get pulled out and be replaced or substituted in place of this product the coefficients of c divided by a. We're almost done, of course. We're ready for that substitution, but we do want to get this pesky coefficient of 2 out, so we just have that x sub 1 plus x sub 2. So yeah, just factor it. So 2 times x sub, now this is addition, so it's commutative. I'm just going to turn this around. X sub 1 plus x sub 2 over x sub 1 times x sub 2. And there's our sum and product of our roots for this quadratic. So we're ready to substitute and just simplify what's left. We have 2 times the sum of our roots, which is the opposite of coefficient b over coefficient of a. So it's the opposite of 1 over 5, divided by the product, which is going to be equal to the quotient of the constant divided by the leading coefficient. So over 3/5. And hopefully you're good with fractions by now. I don't really know what math class you're studying at the moment, but this is 2 times negative 1/5, or 2 over 1 times negative 1/5. So we're going to multiply the numerators. We're going to multiply the denominators. So we have negative 2/5 over 3/5. You may know that these common denominators, the denominators of 5 in the numerator and denominator are going to cancel, but just in case, we have our main fraction bar here. We have negative 2/5 divided by our denominator of 3/5. Of course, we don't really divide fractions. We multiply by those reciprocals, or the reciprocal of the second factor. So we're looking at negative 2/5 times 5/3. 5 divided by 5 is going to cancel, and we have negative 2/3. So given that, and double check, yes. So given that we have this quadratic equation of negative 5x squared plus x plus 3, and without solving that, because maybe with a higher order polynomial it would be very hard to solve, we're going to evaluate this expression of 2 over x sub 1 plus 2 over x sub 2. Turns out that it's equal to 2/3. So I could evaluate some expression based on roots of this polynomial without having to solve that polynomial. Very, very cool. I got 2 more examples coming up right now. No. Alrighty then, we have the same quadratic and we have a different expression that we're going to evaluate. Again, sum and product. All we can look at, or that we need to develop out of this expression, and there are no powers of 2's on any of those terms. So we have possibly a bit of an issue, the fact that x sub 1 is squared and x sub 2 is squared. We're going to go through the same process of finding that common denominator, though, because we have our 2 separate terms. And adding 2 fractions and making 1 sure worked on the first example, so let's give it another try. We're going to multiply x squared, or x sub 1 squared to the numerator and denominator, and x sub 2 squared to the numerator and denominator as well. And that is going to give us x sub 2 squared plus, and then remember we're going to bring this over numerator and denominator, so plus x sub 1 squared over x sub 1 squared, x sub 2 squared. Well, dealing with that power of 2 in the denominator is really actually quite simple. Let's just write it as x sub 1 times x sub 2 squared. We're going to have a bigger issue in the numerator, though, because powers of 2 on our sum, powers of 1, this is not equal to negative b over a. It's not equal to, good Lord knows what my kids have come up with. It's not negative b over a squared. Yeah. It's also not factorable. And you think, well, okay, because that's how you bring exponents down, is with factoring or division, and we need to get these factors of 2 down to factors of 1. That's something you had to deal with in your trig proofs and pre-calc. Well, if you took trig in your pre-calc class, a lot of students do just take trig as a semester course, but at any rate, I digress. I need to make something a factorable, something quadratic that's going to go down and give me some factors basically that are first degree. Let's see. If I have a squared and c squared, what would need to be in the middle that would allow me to factor or have some kind of factorable trinomial? You know, it really kills me that all the time I get kids writing things like this. X plus 2 squared is x squared plus, well, 4, because I do 2 squared. And I go, no, 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 come on. You're making me just die a little bit inside. When you square a binomial, you are supposed to have 3 terms. Unless it's, yeah, any binomial squared is 3 terms. And you know what? I need to have an x, basically x sub 1 plus x sub 2 somewhere. Hey, so like basically, and let's go ahead and write this. How about we just write this as x sub 1 plus x sub 2 with a power of 2 on it. Why? Because I've got powers of 2 in my numerator. If I expand this binomial out, we're going to get x sub 1 plus x sub 2, x sub 1 plus x sub 2. X sub 1 times x sub 1 is x sub 1 squared. X sub 1 times x sub 2 is x sub 1, x sub 2. Another x sub 1, x sub 2. And then x sub 2 times x sub 2 is x sub 2 squared. So x sub 1 squared plus 2 x sub 1, x sub 2 plus x sub 2 squared. Maybe your book will be nice to you and do something like, I don't know, a plus b or u plus v or something like that. But my book, and I'm staying consistent with it, uses subscript. So this is getting kind of ugly to say. But look here. If I add in a plus 2 x sub 1, x sub 2 term, then I can take these terms that are squared and factor it and get a sum of roots squared. And that's awesome, because then I would know that that sum of roots is negative b over a. Well, okay, I just need to add in another term. But of course, I can't just add some number in. I'm going to change its value. Like, I couldn't just find common denominators by multiplying the denominator by a factor. I had to multiply the numerator as well, so I'd create that identity. I don't want to add in 2 something. I want to basically add 0. So if I'm adding 2 x sub 1, x sub 2, I need to subtract 2 x sub 1, x sub 2. So I change the way the numerator looks, but not its actual value. Now, through my little bit of work over here, or just your vast algebra knowledge, we see that this is factorable, and it is, well, let's just do it in green, x sub 1 plus x sub 2 squared. Now I have a minus 2x sub 1, x sub 2, keep wanting to write x and y, x sub 1 times x sub 2 squared in the denominator. And now I'm at a point where, hey, I have a sum, and I have a product of my roots, and there's no other mess going on. Then the sum of these roots is negative b over a, so we're looking at negative 1/5 squared, and now we have minus 2. We have a product of our roots, which is equal to c over a, which is equal to 3 over 5. And yes, I picked examples that we could practice our skill of fractions. Again, we have our product, so c over a, 3 over 5, and it's squared. So negative 1 squared is 1, 5 squared is 25. We have minus, and this is 2 over 1, so 2 times 3 is 6. 1 times 5 is 5. Over, you're squaring a fraction, you're squaring both the numerator and denominator separately, so 3 squared is 9. 5 squared is 25. We're getting excited. We're almost done. We need a common denominator, so we're going to multiply the numerator and denominator by 5 over here on our second term. And we have negative 1 minus 30 over 25, our common denominator. All of that over 9 over 25. You have, since I showed this step very thoroughly in the last example, our fraction in the numerator and our fraction in the denominator have exactly the same denominator. So when I flip up that 9 over 25 and make it a multiplication of the reciprocal, make it a multiplication of 25 over 9, these denominators are going to cancel out. So we are looking at, whoops, that's a positive 1 and I wrote minus. 1 minus 30 is negative 29 over 9. And to double check that I have not made an error, except for the one that I just caught, boom. That's the end of our second example. Boom, I'm in. Bam! So we've had a lot of factoring examples in review in this video, and we have one more with our last example. We want to evaluate the sum of x sub 1 cubed plus x sub 2 cubed. Yeah, we want to take the roots from this quadratic, cube them, add them together, and find an answer without actually solving the quadratic. Because what if it was a fifth degree and we were extending this concept onto higher order polynomials? Maybe we wouldn't want to actually have to solve it. Well, you're going to have to remember that, again, we don't have any powers, we don't have any subtraction, division. It has to look exactly like the sum and the product of these roots to be able to do just a straight substitution using the coefficients from our polynomial. That means that we have to factor a sum of cubes. And basically, this is just a formula. I mean, there's a way to prove it or derive it, but we need to be able to pull this out of our toolbox and remember that a cubed plus b cubed is equal to a plus b. So you take the cube root of each of those terms, and then that is times a squared. Whatever this is now, you're going to change the sign. So minus ab. Every new school year I have to go look up, is that just a coefficient of 1 there or 2? But it is minus ab plus b squared. So this is equal to x sub 1 plus x sub 2. Well, that's nice. We already got a place that we can plug in our negative b over a times x sub 1 squared minus x sub 1 x sub 2 plus x sub 2 squared. And here we just have the same problem we had in the last example, where we have powers of 2 and on our roots, but in terms of sums, we have to have powers of 1. And like I just showed you, and kind of a hint as how to go through this process, I just wrote out with powers of 2, I wrote out a x sub 1 plus x sub 2 to the second power, expanded, and then saw, okay, well, if I can make my expression look like that, then I can factor it and get into a form that we can use. Keep that in mind as you do your problems in your book. You might have other versions from other than the 3 that I'm showing you. I need that to be a 2, x sub 1, x sub 2, so it factors down to be x sub 1 plus x sub 2 squared. So if I'm going to make that coefficient go from negative 1 to 2, I need to add 3 of these terms. So we have x sub 1 plus x sub 2 times x sub 1 squared plus 2 x sub 1 x sub 2 plus x sub 2 squared. But remember, I had to add 3 x sub 1 x sub 2 to go from negative 1 to 2. So if I'm going to add 3, I have to then subtract 3. So minus 3 x sub 1 x sub 2. So I added 3 and subtracted 3, which is effectively just adding by 0. So I just made this look different. I didn't change its value. So this, once again, like our previous example, is a factorable, it's actually a perfect square trinomial. I want to get all fancy and use some vocab. X sub 1 plus x sub 2. Now this is being factored to be x sub 1 plus x sub 2 squared minus 3 times x sub 1 x sub 2. Good. Got all my parentheses in the right spot. Sum, product of roots. That means we can just go to our quadratic equation, pull out the appropriate coefficients, and for the sum, it's negative b over a. It's negative 1 over 5. Oh, the air just shut off. That's awesome. And we have another negative 1 over 5. I do apologize for the hum in the background as I made this video. But it's Florida, it's summer, and the air conditioner is right out the window. The sum here, we have negative 3 times the not the sum, but the product. So negative 3 times c over a, negative 3 times c over a, so 3/5. Now, just like before, we basically just have arithmetic to finish this question up. We have negative 1/5 times, we have 1 over 25, negative 1 squared, and 5 squared, minus 3 times 3 is 9. Of course, that's 3 over 1. So now we're looking at 1 times 5, multiplying the denominators, which is 5. Come up with our common, go through a process of creating a common denominator so we can add the 1 over 25 and the 9 over 5, and we get negative 1/5. Remembering that we have a denominator of 25 here and a denominator of 25 here, we're just doing 1 minus 45, which is negative 44 over 25. And a negative times negative is positive, so we're looking at 44, and we have 5 times 25 is 125. I'm Mr. True. That is the end of my last example. Bam! Go do your homework.